Hello everyone, I'm Ghulam Aminia from the All-Engineering Institute. I want to present the work generalization error of the graph neural networks in the mean-field regime. This is the joint work with Yushin, Gizina, Lukash, Sam. In this work, we are going to propose a novel framework for generalization error of the graph neural networks with focus on two main framework, which are graph convolutional neural networks and message passing graph neural networks, using functional derivative and radical complexity analysis in the mean-field regime. We are going to derive the generalization error with convergence rate 1 over n for regularized empirical risk minimization using a functional derivative approach. And also we are going to investigating the generalization error of the one hidden layer neural graph neural networks for the purpose of studying the effect of the hidden neurons. Our problem formulation would be X as a graph samples and Y as the labels. We are going to consider binary classification. And also we are focused on the graph classification. Our training data set is that n, and we consider ID assumption. We consider the empirical measure, mu n, and we want to learn a function fw, which is parameterized by a number of parameters from the space of the parameters. We consider the learning algorithm as a mapping of the data measure or empirical measure to a measure over the parameters. The loss function is a function of the measure and data. The risk function is defined as the integral of the loss respect to the data measure, which if we are going to consider the empirical measure would be the empirical risk and or the population measure would be the population risk. The KL divergence and symmetric scale divergence are defined as a KL between the two measure M prime and M. We focus on in this presentation on the graph convolutional network. For this purpose, we introduce the neuron unit, the input pair or the graph sample with n number of nodes, and which are containing F as the node features and A as the graph having symmetrics. The Dmax and Dmin are the maximum minimum degree of nodes among all graph samples. Parameters are W1C and W2C, where the W1C are the parameter of one neuron and W2C are the parameter where connect the output of the neuron to the output of the network. We consider the H as the number of units. Also, we consider the empirical parameter measure MH. And because we are focused on the graph classification, we consider the readout function, which is the average of, for this study, we consider the mean readout or sum readout, which can be the average of the output of the network for each node. And finally, the prediction would be the average of the readout the average of the readout function with respect to the empirical parameter measure. When the number of nodes goes to infinity, this empirical measure over the parameter will converge to a continuous measure. For our study, we can consider, for example, in the binary classification, the logistic loss. Finally, we are interested in generalization error, which is the difference between the population measure and the empirical measure. And we consider, because it is dependent on the data samples, which are random, we are interested in the expected version. We introduced the replace one sample in empirical measure, where the one sample, for example, Z1 is replaced by Z tilde. And we based on the result in the reference Aminian et al. The expected generalization error can be represented as the difference between the loss function were evaluated as at the replace one sample, and the loss function where the measure is dependent on the empirical measure, the replace one sample empirical measure, and again evaluated at replace one sample. And for our problem, we consider the K-regularized problem because the solution of this problem is unique due to the strong convexity of the KL and assumption of the convexity of the loss. The solution to this problem would be the Gibbs measure, as shown here. And for our theoretical result, we have some assumption where the bounded loss function or bounded gradient of loss function, the loss function convex, and bounded neuron unit function, and bounded node features. Our main result are first one upper bound on the generalization or expected generalization, which is general, and then using the concept of the Gibbs measure, we can derive a lower bound using some methods based on the KL symmetrized divergence. Finally, we can derive a parametric upper bound over the expected generalization error of the Gibbs measure, which has the convergence rate of 1 over n. Finally, we can compare our result with the previous result as shown in this table. For example, when many of the previous results depend, the transition error depends on the width of the layer or width of the hidden layer, and that they can be vectors when the edge goes to infinite. And we also can derive the convergence rate of 1 over n. In the experiment, we also try to demonstrate that when the number of nodes goes to infinite or getting large, the generalization error is going to decrease, where we can observe that the previous result on generalization error can be vectors when the number of nodes getting large. However, the result shows that the generalization error would increase with the number of nodes. For this experiment, we consider stochastic block models and the Shreni and protein data set, and we are going to increase the number of nodes S and the effect of that on the true generalization error. This observation shows that the upper bound depending on the width of the layer fail to capture the trend of the generalization error in the over parameterization regime. Finally, you can see our work with more details at the following QR link. You can also we can also explore our GitHub. For more details, you can contact us. Thank you so much for your attention.